Once again, we have 10 total tests, quote-unquote tests. Not all of them are really tests. Some of them are just forms, like the geometric series. And our next pair of tests are comparison tests. One is called the direct comparison test, and that's the one we're working on right now, the direct comparison test. And the idea with the direct comparison test is that if you have a series that's close to a p-series or close to a geometric series, a lot of times we can compare to a p-series or to a geometric series. So if it looks really close, a lot of times we can do this comparison idea. And so the basic principle we mentioned at the end of class on Tuesday, smaller than converging will converge, bigger than diverging will diverge. Those are our two basic principles. And then in terms of practice, we always are thinking about analyzing the A sub k series. So that's the series that you're given. And you're told, figure out, does it converge or diverge? The B sub k series, we make this one. This is one that we conjure up. We conjure it up, and that's going to be one that, so we know that B sub k series converges or diverges. We pick it so that it converges or diverges. Okay, so when we look here, here is an example of a B sub k series. We know that series. That series is a convergent P series. P is 2. That's bigger than 1. For a P series, bigger than 1 converges for a P series. And then we look at this series. This series right here is not a P series, but it's really close to a P series, right? It's P series-ish. We just have that 10 right there, that nagging 10. And we know that adding 10 in the denominator is not going to change whether it converges or diverges, but we still have to go through the math to prove that it converges. And so here we can see visually like, oh yeah, here's a converging series, we know that. Here is a series that is smaller than it, term by term. So if we look at all the terms, right, this term down here is smaller than that term, this term is smaller than that term. So the black dots are progressively smaller than the red dots, so it must converge. That's the comparison test, the direct comparison. And similarly for a diverging setup, here again, this is a p-series. 1 over k to the half. In this case, k is equal to 1/2. And 1/2 is less than 1, therefore we have divergence. I said k equals 1/2. It should be a p equals 1/2. So p is equal to 1/2. As soon as you write p, I know that you've identified it as a p series. So we look at that, p is 1/2, that's less than 1, therefore it diverges. Right? So for p, bigger than 1 converges, less than 1 diverges. Geometric series is opposite. Less than 1 for a geometric series converges, greater than 1 diverges. So it's the opposite. Because in a geometric series, this is in the numerator. In a p series, that's in the denominator. So small numerator converges or big denominator converges. All right, and when we look here, so there's our divergent series. That's the B sub k. That's the one we choose. It's going to be our comparison. And then we look at this thing up here. It's like, okay, it's not a P series, but it's really darn close to a P series. All we have is this subtraction of 3. We know that in the big picture, that's not going to derail convergence or divergence. And so here we have the same type of picture. We have the black dots diverging. The red dots are bigger term by term, so that series must diverge also. So you can use diverging to show diverging. You can use converging to show converging. All right, so let's try a couple. So once again, there's P series. P is 2, greater than 1, so it converges. Now, the direct comparison test is not always going to work. So let's think conceptually for a minute. if we know that this p-series converges, and then we come down here and we want to decide whether this series is smaller than it, here's how I think about it. This denominator is bigger than that denominator, which means the fraction values are smaller. So this one is smaller than that one. So we will be able to use the direct comparison test to show that this one converges. But then you go to this one, and the denominator is smaller than the k squared because we subtracted off one, which means the fraction values here are bigger than the fraction values there. We cannot use the direct comparison test in that case. We can't use the direct comparison to show that a greater series converges. Right? We have to have smaller than converging. So here's how we're going to do the math. So once again, we call this the b sub k. The one that we know is b sub k. The one that we're analyzing is a sub k. And here's how I'm going to write this. So what I want to show, so WTS, I want to show, let's see, these are the ones I'm analyzing. I want to show that those are smaller than, and you can say greater than or equal to, the b sub k's. So the b sub k's we have as converging, it's a convergent series. We're analyzing these a sub k's, this a sub k series. That's what we want to show. If we can show that that's true, if we can show that smaller than b sub k is true all the way through for all the k's, then we have smaller than converging, so it converges. So let's see. So then we just plug it in, and the math for the direct comparison test is usually pretty easy. It's usually just a little bit of algebra. So we don't know, so I'm going to put a question mark here. That's what we want to show. We want to show that the a sub k's are smaller. And usually it's just a couple of steps. I'm going to cross multiply. So multiply both sides by k squared. Multiply both sides by k squared plus 1, also known as cross multiplication. And you can then subtract off the k squared. And we can always get down to an inequality that we can solve by inspection, or at least most of the time. So we get down to that inequality, which is true by inspection. And so since this is true, therefore, the a sub k series converges. So a sub k series is the one that we're analyzing. So we've shown that that converges by direct comparison to the b sub k series. Smaller than converging converges. Now if we look at this thing, let's just suppose that we're blindly trying to apply the direct comparison test. If we're blindly trying to show it, we know that this thing is going to converge. It's p-series-ish. So we would want to be able to show this. And what we are going to see here is that we're not going to be able to show this, that this inequality is not going to hold. So we take our a sub k. We don't know. Is that a sub k? Oops, that's supposed to be a minus 1. Is that going to be less than the b sub k? So we try to show, this is what we would like to show. We do our cross multiplication. And when we're doing this cross multiplication, keep in mind that we're multiplying by positive expressions, so we don't have any inequality jumping. Right? The k is an integer bigger than 1. We can't even, actually, this is a bad thing. This k really should start at 2, right? Because that causes division by 0. So we get k squared less than or equal to k squared minus 1. We subtract off the k squared. We get 0 less than or equal to negative 1. This is false. So therefore, direct comparison test, DCT, doesn't apply. Don't apply? Doesn't apply. So we can't use the direct comparison test. Or you can say that it's inconclusive. So that means we would have to do something else. And what we are going to see is that in a case like this where the direct comparison test doesn't work, what we'll have to do is use something called the limit comparison test, which we'll get to. Okay, so the direct comparison test cannot be used to analyze a larger series if we're trying to show convergence. Bigger than convergence is not definitive.
Is it the same if you're trying to prove divergence and it's smaller?
Yes, exactly. Yeah, so divergent, if we want to show something that's divergent, bigger than divergent must diverge, but smaller than divergent, it could diverge or it could converge.
Okay.
Right. So let's take a look at this. So for series that we suspect converge or diverge but don't meet the inequality requirement, the limit comparison test might be the ticket. So let's see how this works. So the idea here, once again, the B sub k's, this is the known series. This is the series we are using as our comparison series. And so we'll have to talk about, well, how do you create it? How do you choose the B sub k? And then A sub k, this is the one that we're analyzing. This is the one that we're analyzing for convergence. And this one we know. All right, so the idea here is going to be if we form the ratio A sub k over B sub k and take the limit and we get a positive real number. So down here we say that if L is between 0 and infinity, that means that it's a finite positive number, it's a positive real number. That's what we're saying there. So if we use the notation I introduced on Tuesday, we would say that L is an element of the positive reals. So it's not 0, it's not infinity. Positive real. If this limit is a positive real, it means that the two series are linked. It means they're both diverging or they're both converging. It means they're doing the same thing. So if there is a positive limit for their ratio, that means they behave in the same way. They either both converge or both diverge. Now if we get one of these extreme cases where we have L is equal to 0 or infinity, we have to analyze it a little bit more subtly. You're not going to see a lot of these. Let me just try to explain it and see if you can get the idea. So we've sort of agreed that you can show a series converges by comparing it to another convergent series. We've agreed that you can show that a series diverges by comparing it to another divergent series. So keep that in mind. You can't use something that diverges to show something converges and vice versa. Converge and converge or diverge and diverge. So let's think about this. So if the limit is 0, okay, and we're trying to analyze the A sub k series, okay, we're trying to analyze the A sub k series, and we suspect that the A sub k series converges. So we always are going to choose converge and converge or diverge and diverge. So if we suspect the A sub k series converges, we're going to choose a B sub k series that converges. And if this limit is a positive real, we can conclude that the A sub k series does in fact converge if this limit is L. Let's think about why. So for this to be a number L, if the B sub k's converge, it just means that if this limit is 0, not a positive real actually, I'm sorry. Positive real is just for 1. For 2, the limit is 0. So if this limit is 0, and we have a B sub k series that converges, isn't the limit of B sub k 0 if the B sub k series converges? Right? Any series that converges, the terms have to go to 0. So if we're choosing a B sub k series that converges, we know the limit of B sub k is 0. Right? Now the only way that this limit could be 0 then is if the denominator is going to 0. If the overall limit's going to be 0, it means the numerator is going to 0 even faster. right? It's the L'Hopital rule type of thing. If both are going to 0, but the overall limit is 0, the numerator must be going to 0 faster. So what we're saying then is that the a sub k's are going to 0 faster than the b sub k's, and if the b sub k's converge, then the a sub k's must converge also. Okay, so if the limit is 0, and we're trying to show convergence, we pick a b sub k series that converges, so those limits are 0. The limit of the b sub k's is 0. And if this overall limit is 0, the a sub k's are going to 0 faster, so they must also converge.
What if your limit is divided by 0 error?
So that's a L'Hopital's rule type of thing, right? If both the numerator and denominator go to 0, you have to do something. Cancel a common factor, take the derivatives, or whatever. Okay, so next one, if the limit is infinity, and we suspect that the a sub k series diverges, if we suspect it diverges, we're going to use another divergent series to compare it to. So we're choosing a b sub k that diverges. All right. And now we look at this limit, and if this limit is infinite, and the b sub k series diverges, that means the b sub k's are not going to 0 very fast. They have to be going to 0 if we even are considering convergence. So, but the b sub k's are not going to 0 fast if the b sub k thing diverges. And if this limit is infinity, that means the numerator is behaving even worse, right? The numerator is going to 0 slower than the denominator. So then we're going to get divergence. Does that make sense? So if this limit is infinity, that means the b sub k's in the bottom have to be going to 0 faster than the a sub k's are going to 0, which means if the b sub k series diverges, the a sub k series must diverge because they're going to 0 even slower. All right? So think the harmonic series. The harmonic series, the terms are going to 0, but they're going to 0 slow. Okay? They're going to 0, though. So the numerator is going to 0 slower. The numerator is always bigger than the denominator. If the denominator is going to 0 faster than the numerator, then that limit's going to be infinity. All right, so now these two extreme examples here, you're not going to see them much. The heart of what we're doing is this. But, think about those. Those are two kind of advanced ideas to think about. All right, so let's do sort of the core of the limit comparison test. So we know, air quotes, that this series is going to converge because it's very close to a p-series that converges. But we just showed a minute ago that the GCT does not apply because these terms are bigger than one over k squared. So we can't apply the direct comparison test. So here's how we apply the limit comparison test. So the limit comparison test, we're going to take the limit as k goes to infinity of a sub k over b sub k. So the a sub k is always the series that we're analyzing, so we're going to put that in the numerator. And then we divide by the b sub k, which comes from the series that we conjure up. And hopefully it's pretty obvious why we would conjure that one up. The -1 is insignificant, and so we kind of just get rid of the insignificant parts of this summand. And what's left is the b sub k. So then we do our copy dot flip thing. Flip the denominator fraction. And what is that limit as k goes to infinity? 1. And this, not to be confused with a geometric series or a p-series, with the comparison test, the limit comparison test says if this is a positive real, both series do the same thing. If that's a positive real, it means they're linked together and they're both dragging to infinity and diverging or dragging to zero quickly and converging. So therefore, both series converge. Since we chose a B sub k that converges, the B sub k series converges, and the A sub k series converges as well. So if you get a positive real. Yeah?
Will you have to like, sometimes like prove that A series converges, diverges, and then use that?
Wait, say that again?
Prove that B of K converges, and then analyze A of K.
Yes, yeah, that's what we were doing. So we already talked about the B sub k series on the previous slide. This is converging. So we say that this is how we justify that it's converging. We identify P, point out the fact that it's greater than 1. That means that this converges. So that's a convergent P series. And then we're using that convergent P series right there to compare to the A sub k. Make sense?
You
Yeah.
have to prove that it is a convergent or divergent series to use it for a comparison test.
Absolutely. So we are only going to use series that we know instantly whether they converge or diverge.
An
So if
easy
it's a
series.
P series or a geometric series, those are the two. For a P series, if P is bigger than 1, we know it converges. If it's not bigger than 1, it diverges. For a geometric series, we know that the ratio less than 1 in magnitude converges, otherwise diverges. So those are the two series that we can analyze by inspection. So those are the ones that we typically choose for the B sub k. So let's look at this one. So here's a new one. So let's write down B sub k. So we suspect that this series diverges because it just looks like a slightly tweaked harmonic. Adding the 1 in the denominator isn't going to change convergence or divergence. And so the B sub k series that we're going to choose is going to be the harmonic. We essentially erase anything that's insignificant. And you can say that this diverges because it's a harmonic. It's a divergent harmonic. You could say that. Or you could say, oh, this is a P series. P is equal to 1, which is not greater than 1. So it diverges. So either way is totally fine. Somehow you have to indicate on the test why your B sub k diverges. So you can say it's diverging because it's a harmonic. That's accepted fact in here by now. Or you could say, oh, it's a P series where P is 1, therefore it diverges. If P is greater than 1, it converges. If P is not greater than 1, it diverges. So there's our comparison. So now we go to the want to show step. So we want to show that the A sub k's, those are the ones we're analyzing, we want to show that they are bigger than the B sub k's. Because the B sub k series diverges. So if we can show that the A sub k series is step-by-step bigger than it, then it must also diverge. All right, so what we want to show is this. And we'll see if we can show it. So that's what we want to show. You know, and intuitively we say to ourselves, oh, the denominator here is bigger, so the fractions are smaller, right? So are we going to be able to show that this is true? Oops, nope. So what do? This is false. All right, so now we go to the limit comparison test. So direct comparison test fails. It's inconclusive. So this right here, this tells us that the DCT is inconclusive. And that tells us go to the LCT. So that means take the limit as k goes to infinity of A sub k divided by B sub k. So we'll take the limit of A sub k, that's the one we're analyzing, 1 over k plus 1. We divide by B sub k, we're dividing a fraction by a fraction, so we multiply by its reciprocal. And what's that limit? 1. And this is a positive real, therefore both diverge. since the b sub k that we chose diverges, and we get a limit that's a positive real, then both do the same thing. They are quantumly joined. All right, so we couldn't show bigger than diverging diverges here, but we can use the limit comparison test to show the next best thing. They are doing the same thing, diverging. So now you may say, why don't we just use the limit comparison test all the time if it seems to work when the DCT doesn't work? And the answer is there are actually some series for which the limit comparison test will be inconclusive, but the direct comparison test will be conclusive. So there are examples of that. Moreover, the direct comparison test gets more at the underbelly of what it means to converge and diverge, so it's super important to go through this process to try to reinforce these ideas of infinite series. You know, showing that less than converging converges, greater than diverging diverges. And if that doesn't work, then think of the limit comparison test, you know, as the last resort if you can't do it with the direct comparison test. All right, any questions on those examples thus far? Okay, let's take a look at. So it says use the comparison test or the limit comparison test to determine whether the following series converge. All right, first off, let's choose our b sub k. To choose the b sub k, the general rule of thumb is to remove the insignificant terms and simplify. That's the general rule of thumb. So when we look here, the adding of the 3 is insignificant. So we think of this as k to the half over k squared. So what we want to choose for our b sub k, we want to simplify this. We're going to take away that 3, and then we're going to simplify this, and this will turn into 1 over k to the 3/2 power. Yay. So does the b sub k series converge or diverge?
Converges.
So we have 1 over k to the 3/2. We're going to identify p as 3/2, so make sure you identify your p if you're going to use a p series as your comparison. Make sure that you use the letter p. So I know that you know this is greater than 1, therefore converge. So if our b sub k series converges, what do we think a sub k is going to do?
Converge.
Converge,
Hopefully.
right? Yeah, just adding this little 3 in the denominator should not change things. So we want to start with the direct comparison. So the direct comparison, this is what we would want to show. So let's see, direct comparison test. We would want to show that the a sub k, so if we're trying to show convergence, we want to show that they are less than the b sub k's. Okay, so just plug in what we have. We have the square root of k over k squared plus 3. This is what we would like to show. We'll put a question mark because we don't know yet. And that's 1 over, it's that. Now, if we're clever, this b sub k right here was simplified from that. It might be easier to actually use the unsimplified b sub k, because then we can cancel some things pretty easily. And so right away, remember that k is a positive number, so we can divide out the root k's. Those are positive, so we can divide them away. And then we can do our cross multiplication, and we get that k squared less than or equal to k squared plus 3. So cross multiplying, k squared plus 3 goes to the right, k squared goes to the left. And if we subtract off the k squareds, we can always get down to something that we can solve by inspection. This is true. So that allows us to conclude both series are going to converge. Both converge. So direct comparison in this case worked. The intuition behind it, this denominator is bigger than this denominator. Therefore, the fraction values there are smaller. Bigger denominator, smaller fraction, smaller than converging converges. Yeah?
And the square root of k. Can you explain that to me again, please?
Division. So because the k is positive, we can divide both sides by root k. Or multiply by 1 over root k. We don't have to worry about any inequality changes because everything's positive. And so you can think of it as dividing it out, or you can think of it as multiplying both sides by the reciprocal, and it'll go away. So either of those concepts. Okay. Make sense? And that's why it's helpful to leave it in this form. It would still work if you left it in this form. You just have some other simplification later where you'd get to the same place.
All it does is then you cross multiply and you end up with k to the 3/2 times k to the 1/2.
And you add those and
Adds and cancels.
adds and cancels and ends up in the same place.
Exact same place.
All right, let's take a look at this thing. So the b sub k is actually a lot easier to choose than it may have seemed at first. Like, where do you get this b sub k series? Well, we're doing the same thing. We're going to say, okay, that 3 is insignificant, so we would like to compare it to, we're going to choose for our b sub k, we're going to choose just 1 over 5 to the k. Now, what kind of series is that? So it's an exponential form, which is a geometric series. So it's not a p series, right? With a p series, the k is in the base, not in the exponent. Right? Here the k is in the exponent. And so what we would do is rewrite it in geometric series form. That is how we would write the geometric series. Geometric series is a r to the k when you look at the summand. All right, and this one starts at 1. So we could put a 1 down there. Could put k equals 1, doesn't matter. We know it's an infinite series, but it starts at 1. Now, it doesn't even really matter where it starts because we don't care what this geometric series converges to. We just care whether it converges or diverges. So let's identify the r value. And as soon as you write down an r, I know that you're identifying it as a geometric series. What is the common ratio here? 1/5. And for a geometric series, if that is less than 1, therefore converges. Right, for a geometric series, less than 1 converges. So our suspicion then is that the a sub k series diverges. Excuse me. The a sub k series converges. Going to do the same thing. So let's see. If we're going to try the DCT first, which is always the best strategy, then we want to show, if that converges, we want to show that the a sub k's are smaller than the b sub k's. That's what we would like to show. Because our b sub k series converges, our suspicion is that the a sub k series converges, so we would love to be able to show this. And are we going to be able to show that?
Yeah.
Because this denominator is bigger. Right? The 5k plus 3 is a bigger denominator, so the fraction values are smaller. So yeah, we will be able to show this. We'll do our cross multiplication business. And then we can subtract the 5 to the k's, and we end up with this numerical inequality that we can solve by inspection. That is true. Therefore, both series are going to do the same thing, so they both converge. So direct comparison. Any issues? All right, let's change this one a little bit. So let you all work on this one. So let's suppose instead of instead of an addition by 3, let's suppose we subtracted 1. And it doesn't matter where the series starts. So you all try that one. So first do the direct comparison, and then if that doesn't work, then jump over to the limit comparison. Let's see what happens. Let me know if you're running up against anything. The B sub k should match with the last one. Just erase the -1.
So you get this, I know it was one from the last one, what's the math there?
Divide by the dominant term.
So we're gonna divide by 5.
5 to the k, right?
So you get 1 over 1 minus 1 over 5 to the k, which is 0.
Yeah, exactly. Yeah, so even though we use that same idea that if everything was polynomial, you divide it by the highest power of x, it's the same idea. The real concept is that you divide by the dominant term.
I needed that.
We're almost there. You can take a break.
And you could also use L'Hopital's there, right?
And you
To
could
show
use-
that it's just 5 over k ln, or ln 5 over.
Yep, you
The
could.
same thing.
L'Hopital's would work great also because the 5 to the k's will cancel.
And you just end up with 1 over.
So the first thing you want to do is identify the b sub k.
If I don't remember the simple math, I can do the complicated stuff.
Yes.
That's
At least the complicated stuff will always work.
Always.
That is the benefit of L'Hopital's.
so there is the b sub k again, and we know that this is a geometric series, so we identify r, we compare it to 1, we make our conclusion, so therefore we have convergence. And of course, with the direct comparison, we're not going to be able to show that this is going to hold. For the direct comparison, we would want to show that a sub k is smaller than b sub k. We're not going to be able to do it. So we'll just write out the math. So 0 less than or equal to -1, false. So if we end up with false for the direct comparison test, then we go to the limit comparison test. And we're going to take the limit of a sub k divided by b sub k. And so that's going to be the limit. A sub k is the one we're analyzing. So 5 to the k minus 1 in the denominator. We're going to divide by the b sub k. The b sub k is exactly the same except the minus 1 is gone. You could think of this as 1 over 5 to the k. Right? Either way, those are the same. So if we think of it in this form, if we're dividing by that, we multiply by the reciprocal. If you multiply by the reciprocal, you get a 5 to the k in the numerator. So here's where you have the two choices. And the most common strategy for limits at infinity, if you divide by the dominant term, if we divide everything by 5 to the k, we have that. And this limit at infinity, this fraction here, this mini fraction is going to go to 0. Numerator is constant, so that's one of our basic limits, is when the numerator is constant, the denominator is exploding, the fraction goes to 0. So this overall limit is then 1, which is a positive real. And if it's a positive real, both series do the same thing, and since the b sub k series converged, we know that in fact both of the series converge. So that is using the limit comparison test. Let's talk about what was mentioned a minute ago with this limit thing here. So you could approach it this way also. So if you have limit 5 to the k over 5 to the k minus 1, you can notice that it is an indeterminate form that satisfies L'Hopital. So we could say, okay, we have infinity over infinity. So we are going to use L'Hopital's rule. So L'Hopital's rule says take the derivative of the top. Derivative of an exponential is itself, multiplied by the derivative of the exponent, which is 1, multiplied by the natural log of the base. And in the denominator, you get the same derivative, because the derivative of -1 is 0. So you're also going to get a 5 to the k times natural log of 5. So that, of course, everything cancels. You get a 1. Same conclusion. Positive real. Positive real means both series do the same thing. So you can do that limit either way. Any questions on the steps?
Yeah, can you go over that, taking the dominant?
So the dominant term strategy is very similar if you recall that if you're taking a limit at infinity, so let's suppose we're taking the limit as x goes to infinity, and we have something like x cubed plus x squared minus 1 over x to the 5 plus x cubed plus 3, something like that. What we do here, we grab the x to the 5th, and if we divide everything by x to the 5th, so if we divide everything by x to the 5th, this becomes 1 over x squared, 1 over x cubed, 1 over x to the 5th. So we're just coming through and dividing everything by x to the 5th. So we're basically distributing a division by x to the 5th, top and bottom, which is multiplying by 1. Does that make sense?
Yeah.
So then where do these 5 fractions all go?
0.
They all go to 0. So we're going to end up with the limit of 0 in the top, 1 in the bottom. So I really shouldn't write it that way. So the limit of this, let's do this. These all go to 0. That goes to 0. That goes to 0. So the limit of 0 divided, well, I guess we can write it that way. That's not bad. That's not bad. I'm not writing division by 0, so that's actually fine. So we could do that. So that limit will be 0. So it's that same idea. So over here, instead of it being powers of x, we're just thinking to ourselves, okay, let's divide everything. This term is dominant. 5 to the k is dominant. So we're going to divide top and bottom by 5 to the k. And that's usually a pretty good algebraic strategy to evaluate the limit. Divide by the dominant term. Okay, so insignificant is relative. You know, like adding a 1 or a 3, we would all agree that's insignificant. Now, when we look at this, The 2 to the k is an exponential. That doesn't feel insignificant, but compared to 3 to the k, 3 to the k is going to grow way faster than 2 to the k. If you start looking at graphs, 3 to the k is going to really go a lot faster than 2 to the k. And so what we want to do is sort of be flexible with our concept of insignificance. So here, what we're going to do is choose the b sub k to be this. Because we are thinking, okay, the 3 to the k dominates the 2 to the k, so let's just get rid of the 2 to the k and see what happens. And right here, it's really tempting. You've got to keep it clear in your mind the difference between a geometric series and a p-series. So the difference is where the k is. The k is in the base of the denominator for a p-series. This k is in the denominator, but it's not in the base, right? It's in the exponent position. And that means that this is actually geometric. So we could write this like that. So geometric is when the k is in the exponent position. P-series is when k is in the base. So a p-series, the denominator is a polynomial. A geometric series, we're dealing with an exponential. Right, so geometric, k is in the exponent, that's exponential. P-series, k is in the base, that's polynomial. All right, so to identify this as a geometric series, we're going to say that r is equal to a third, which is less than 1. So what's our conclusion for less than 1? Converges. So think in your mind, you have fractions, proper fractions, being multiplied by themselves. A third times a third is a ninth. A ninth times a third is a 27th. Right? So geometric series less than 1 means converge. So we're suspecting that this thing up here converges. The a sub k series, we suspect that it converges. So let's first try the direct comparison test. So the direct comparison test, we would want to show that the a sub k is bigger or smaller than the b sub k's. Smaller if we're trying to show convergence. So that's what we would like to show. That's what we would like to show. If we can show that, then we know the a sub k series converges by comparison. So we look at our a sub k, so now we just fill in the blanks. Here's a sub k. We don't know, is it less than? We don't know, we're going to try to find out. We have that. We're going to do a little cross multiplication. So we'll have 3 to the k on the left. And on the right, we'll have 3 to the k minus 2 to the k. The 3 to the k's we can subtract away. 3 to the k minus 3 to the k is 0. So now we have this situation. Is that true or is that false?
Nope. It's false.
That is false. So the right-hand side is negative. That negative sign is not touched by the k. That negative is out in front of the 2 to the k. So the right side is negative, the left side is 0, so this is false. So the direct comparison test is inconclusive. So if that's inconclusive, then we go over to the limit comparison test. So we're going to come over to limit comparison test. And let's actually just think about this with our brains for a second. This denominator is smaller than this denominator. Do we agree? We're subtracting something off. So this denominator is smaller than that denominator, which means these fractions are bigger than those fractions. And since this series converges, that's not going to help us. Bigger than converging is not going to help us. So that's what this concluded. Bigger than converging was inconclusive. So now we come over to limit comparison test. We're going to take the limit of a sub k divided by b sub k as k goes to infinity. So a sub k is the original. We're going to have the limit of that original That puts a 3k minus a 3 to the k minus a 2 to the k in the bottom. So there's a sub k. And then we're going to divide by b sub k, which means multiply by its reciprocal. So that's going to put a 3 to the k in the numerator. So now we have that. We could use L'Hopital's rule here, but L'Hopital's rule is not going to play out quite as nicely as it did with the other one. Here, we really do want to divide by the dominant term. So if we divide everything by 3 to the k, we will have that. So we're going to divide the numerator by 3 to the k. We're going to divide the denominator by 3 to the k, which is really just multiplying by 1. When we simplify, divide 3 to the k by 3 to the k, we get 1. Divide 2 to the k by 3 to the k. 2 to the k over 3 to the k is 2/3 to the k. Now we take our limit as k goes to infinity. And where does that 2/3 to the k go?
0.
0. Because that is an exponential with base less than 1. Multiplied by itself, it gets smaller and smaller, approaches 0. So that tells us our limit is 1. Gosh, we've had a lot of limits equal to 1 today. That limit is a positive real number. So that is a positive real. Therefore, the series are linked. If that limit is a positive real number, it means that they're linked together. They're going to do the same thing. So therefore, both of them are going to converge.
Just forgot to include a convergence. If k equal to 2 from like the initial,
Yep.
then we could have stopped at the DCT, or no?
Say that once again. If
Instead of k equals 1, it was k equals 2?
here,
Yeah.
no, we would still. So where the index starts isn't going to matter.
Okay.
Where the index starts, because the convergence of a series depends on the tail. So it doesn't really, they could even not put that there, and we would still end up with the same conclusion.
And when you look at the DCT, it doesn't really matter what k is. We just know that 0 will never be less than -2 to the k. So it doesn't really matter what k is. K could be a negative number, and it would still be a negative value, which is still never going to be greater than 0.
Yeah, because this minus sign right here is out in front. It's not part of the 2 to the k. So if k is it doesn't, 2 to the k is always positive. An exponent can't make a base negative. Right? So if it's 2 to the -5 or 2 to the 5, both of those are positive.
If you have a complex number where but one part is negative, one part is positive, is it negative or positive?
Complex numbers do not have signs.
So 1 minus I.
So this is an interesting thing. So the real numbers are ordered. If you pick two distinct real numbers, you can put them in order. You can say one is bigger than the other. Less than, greater than, that just means the system is ordered. Complex numbers are a set of numbers that are not ordered. You can't list them in an order. You can talk about which one is further from the origin, or maybe same distance from the origin if they fall in a circle. But the complex numbers are not an ordered set of numbers. The rational numbers, the real numbers, the irrational numbers, those are all ordered. You can put them in a list. But the complex numbers are a non-ordered set of numbers. So order is the concept there. All right, you all try this one with that same kind of idea. You see the k there, and you see the square root of k there. All right, square root of k doesn't seem insignificant, but compared to k, it's more insignificant than not. I'll start rolling through the direct comparison tests and let's just see. We would want to show that the A sub k's are less than or greater than the B sub k's. Larger, yeah. Because the B sub k series, the one I chose right here, I got rid of the square root of k because it's less significant than the k. The 2 in front doesn't matter. So let's see what happens here. So we would want to show the A sub k is the one we're analyzing. A for analyze. We don't know, so we put a question mark. So we get that. Now, when you multiply, you do this cross multiplication business, you kind of get into this weird no man's land here of if you, let's do this. I'm going to add the root k to the left, and I'm going to subtract k from the right. And is that true or false? False. That's false. Right, the square root of k, eventually, like if you don't look close to the beginning, square root of k goes like this, k goes up, y equals k goes up. So this is false. So then we would go to the limit comparison test. But let me point out one thing that is possible here. There are many choices for B sub k. You could choose something slightly different. What about if you chose for your B sub k, instead of getting rid of that 2, like what we're noticing here is that this and this, unfortunately, they're not canceling each other out, right? That's kind of the rub here. But you could, if you wanted to, you could choose this series. Doesn't that series also diverge? Right? This series here, if you wanted to, you could pull out the 2 in the denominator. And you still have a divergent series. Multiplying by 1/2 doesn't change the nature of convergence or divergence. So you could choose this one. And let's just notice that our alternate DCT, if we did it this way, so second try, so let's try this and just notice how different it is. We still want to show the same thing. The B sub k is just a little different. We still want to show that A sub k is bigger than B sub k. So the A sub k is the same. And we want to show less than. Now our B sub k is 1 over 2k. And this changes things quite dramatically. We get that. Now we can subtract these off, right? 2k minus 2k is 0. And if we add the root k to the other side just for grins so that we're not dealing with any negatives, we get that. And that is true. And so if we chose this B sub k, therefore both do the same thing. Since we chose a divergent series, then both diverge.
And could you not pick any constant to throw out front, like 1/10,
100%.
1,000?
Right.
And then just
Any constant that might allow you to get a cancellation in here that's useful.
because multiplying by a constant does not change the nature.
Multiplying by a constant does not change the nature of converge or diverge. Yeah. All right, let's go ahead and take a break,
And
and we can talk about the limit comparison
1,000
test on that one after.
Definitely bigger than 2k minus a root k.
Pause.
Like, oh no, what did I
I'm
do?
insulted.
And if he's pulling over like April Fools.
I prefer the alternative, they pull me over, they give me all this ticket, and they're just like, ah, I prefer you do
That'd
that.
be great. Getting tickets is brutal.
That's why you don't stop.
And then you get free ride to jail.
Yeah, you get free lunch.
It's easy to say where you can do 0 to 100 in 5 seconds.
Free lunch.
Hypothetically, they're gonna stop chasing after people that are going over like 110, so.
Yeah.
Only 110? Second gear, man. No, seriously.
Okay, let's do math. So so with this first DCT that didn't work, if you did want to jump over to the limit comparison test, I just wrote out what the limit comparison test would look like in that case. We still do the a sub k over the b sub k, so a sub k divided by this b sub k would put a k in the numerator there. And then I divided by the dominant term, which is the k. So if you divide the top by k, you get a 1. Divide the bottom by k, you get 2 minus root k divided by k is 1 over root k. And then that little fraction goes to 0, so the limit is a half. That's a positive real. Positive real means they both do the same thing. So you could do it that way as your conclusion instead of modifying your b sub k. So 2 ways there. All right, let's take a look at this one. So most of the time so far, we have had our b sub k found by subtracting off something that's added or subtracted. We can also kind of think of it in terms of multiplication too. And if we think about the k squared and the ln k, the k squared goes to infinity a lot faster than the ln k does, so we think of that as dominating that product. So let's try this and just see what happens. A lot of the series stuff, when you're picking b sub k, you're just trying things, and sometimes you have to modify what you picked. Let's see. So this is a p series with p equals 2. It's bigger than 1, therefore converges. So we suspect that this series converges. That denominator is going to go to infinity even faster than just k squared, so that's what we suspect. So if we go the DCT method, we would want to show that the a sub k's are smaller than the b sub k's. Smaller than converging will converge. So we would want to show 1 over k squared natural log of k. Is that less than 1 over k squared? Cross multiply. And when we cross multiply, there's a couple of ways you could do this. I think it's probably pretty clear the k squareds are going to cancel out one way or another. Those are going to cancel. And so then the question is natural log of k bigger than 1? The answer is, okay, they started at 2, and natural log of 2 is bigger than 1. So even if this wasn't true for the first 2 or 3 k values, as long as it's eventually true for the tail, for all the k's beyond a certain value, that would be sufficient. So this is true already. So that means, therefore, the series that we started with, a sub k and the b sub k, do the same thing. So both series are going to converge. Make sense?
And then what if you have what if k goes up to 300, then it won't determine more?
It will.
If you look at a graph of natural log of k, it's growing towards infinity, and k equals 1 is down here.
It's only not true below 1.
It's only not true, which is
We
yeah,
don't care about
we
it.
don't care about.
It's not the tail.
Like natural log of 1 is 0, so we don't care about that. 1's not even part of this thing because they started us at 2, because 1 would cause division by 0. But
Right, yeah, it's not 1. So,
all right. So use a test of your choice. Okay, this first series is in expanded form. It's not in closed form. That's expanded. And all of these tests kind of require a closed form so that you have an a sub k that you can work with. So let's see if we can write this series in closed form easy enough. So we look at the denominator, we look at the numerator. It's a pretty easy pattern in this case. If we start at 1 and go to infinity, then it looks like this is going to be k over k plus 1 raised to the k plus 1 power. That's a pretty reasonable way to get at it. Does everyone agree with that? Okay, so The question then is, what test should we use? What is the first thing we should always consider, at least mildly, when we look at a series? What is the very first thing that we look at? The divergence test? So if the a sub k's don't go to 0, we know. And when we look at this, if you think about the limit of this a sub k, that's an indeterminate form, isn't it? That's in the form 1 to infinity, which is indeterminate. And if we have an indeterminate form, the 1 to the infinity form is rarely 0. Right? We've seen the 1 to the infinity goes to e, often some sort of modification of e, but I don't think we've seen a single example of 1 to the infinity that goes to 0. So let's check that first. So we're going to take the limit of a sub k, so this is the divergence test. If the limit of a sub k is not 0, then we know it diverges. All right, so we're going to take the limit of all this. Now, we can fiddle with things, and try to manipulate it so that it looks like an exponential, some modified exponential. But in general, and you will have to do this on the test, so let's go through the process here, the log limit process. So we're trying to take the limit of all this. So here's how we would do it from scratch. We're going to define y, and I'm going to change all the k's to x's just because. So we have that. And we know that we want that exponent to come on down. And if we want that exponent to come on down, what are we going to do to both sides? Natural log of both sides. That's the technique to bring that exponent down. So we have the natural log of y is equal to x plus 1 multiplied by the natural log of x divided by x plus 1. Okay. And then we are going to take the limit of both sides, and on the left, the limit's going to go inside because the natural log is continuous and the limit is stealth, so it just slips on in. And then on the right, we know our goal is to put it in L'Hopital form. We know that's our goal. And so let's just take a look at this log thing first. Where does this log thing go as x goes to infinity? Goes to 0. So if we look at this log expression, the inside of the log, the limit of that fraction is 1. Natural log of 1 is 0. So that is going to 0. So we want to create a 0 over 0 if we can. And what we do, which is what we did before when we first started these, we can take this and shove it into the denominator. Multiplication by a factor is the same as division by the reciprocal of that factor. Everyone agree? So if we push that into the denominator, we get 1 over x plus 1. And now we have a 0 over 0 situation. Correct?
Yeah.
And we have 0 over 0. So we can apply L'Hopital's rule. So to apply L'Hopital's rule, we're going to differentiate the numerator and the denominator. Let's go with the denominator first. So this is x plus 1 to the negative 1. So it's going to be negative x plus 1 to the negative 2. So negative x plus 1 to the negative 2. That's that. So there's the derivative of the denominator. The derivative of the numerator, the derivative of a log. First we flip the inside of the log. So the derivative of a log is 1 over the inside in other words, the reciprocal of the inside, multiplied by the derivative of the inside. The inside's a quotient, so we have to use the quotient rule. So I just write it out long form, so it's x plus 1, that's low. The numerator is got a derivative of 1, so there's low, d high, minus high, d low, oh, that's also 1, all divided by low squared. All right, so there is our quotient rule. These x plus 1 squareds cancel. That cancels with that. Right? Division by this reciprocal, if you were to flip it over, x plus 1 squared would be in the numerator, canceling with that x plus 1 squared in the denominator. Okay, so we know that. That's nice. So let's see what's left. So we've got the x plus 1 over x, right there. Let's look at this numerator. This x plus 1 times 1 is just x plus 1 minus x. So this whole numerator, isn't that just 1? And then we have the minus 1 in the denominator. So we have 1 and we minus 1. You could leave it down there for the time being, doesn't matter. And this limit, as x goes to infinity, is negative 1. So we've got the negative right here that's going to be preserved, and the limit of this fraction is 1, so the overall limit is negative 1, which tells us that the limit of y, so the left side has log limit. How do we undo the log now? Exponentiate. So we're going to have e to the negative 1. That is not equal to 0. This is not equal to 0, therefore diverge by divergence test.
Oh, right.
Everyone follow all those steps? Eric? Was that a yes or no?
Yes.
A real yes?
Yeah.
Are we, everyone following the derivative thing here? So our goal is to put it in L'Hopital form, so we want 0 over 0 or infinity over infinity. And when we take the limit of this log part, the limit of the inside is 1, natural log of 1 is 0. This factor out in front can be pushed down into the denominator as a reciprocal. So everyone follow that? You know, like a is the same thing as 1 over 1/8. Right? If you divide by the reciprocal of a, then you'd have to multiply and you get a back up top. The derivative of a log is 1 over the inside, which just means flip the inside. The derivative of a fraction, derivative of a quotient, low d high minus high d low. And then this is just x plus 1 minus x. X plus 1 minus x is 1. And then we have to exponentiate both sides to undo that log. We get something that's not equal to 1, not equal to 0. So that tells us that we must have divergence.
Why?
Now, one good algebra exercise, if the limit of this thing right here is e to the negative 1, there is an algebraic way to manipulate this so that you could use our basic fact. Remember, our basic fact for these e things is that 1 plus a over x to the bx, what does that go to as x goes to infinity?
E to the AB.
E to the AB. So that would be a good algebraic exercise to see if you can, manipulate that so that you could just use that. A little bit of algebra. Keep you sharp. Okay, this thing. 1 over natural log of k. First off, What do you think? Do you think it converges or diverges? Diverge. Because 1 over k, that's kind of our threshold function. We think about that all the time, the harmonic. 1 over k diverges.
V of the k is smaller.
And natural log of k goes to infinity even slower than k goes to infinity. So these fractions go to 0 even slower than 1 over k. So intuitively, we're convinced that that is going to diverge. So what test should we use? If we think about the order of tests, clearly the divergence test is inconclusive because the limit of that is 0. So divergence test is out. The next thing we looked at was the integral test. It's definitely, I guess we looked at telescoping also, but it's not telescoping, it's not geometric. Integral test. Do you know how to integrate that? No. We have integrated natural log of x using integration by parts, but we have not integrated 1 over natural log of x. So integral test is going to get really ugly really fast.
You think you do what? Yeah, I don't think that they, because if there's a 1 over x ln of x.
So if it was 1 over x ln x, then we could integrate it easily. So this we can't. But what we know is that, so when we look at the natural log function, so it's looking something like that. And we look at, when we think of divergent series, the simplest of them all is the harmonic. The simplest of them all is this one, right? Y equals k, right there, or y equals x if we're thinking of it as a continuous function. So there's y equals x. Here's y equals natural log of x. How about if we just try to do a comparison test with 1 over x? Seems like a reasonable thing to try. So let's go ahead and choose a b sub k to be just our harmonic. So, whoops, but we're going to use it as a k when we're talking about a series. So this is a p series with p equals 1. So therefore it diverges, or you could just say that it's a divergent harmonic. Diverges because it's a harmonic. Okay, so diverging with the direct comparison test, we would want to show a sub k is bigger or smaller than the b sub k's? Bigger. So bigger than diverging diverges, so we'd want to show this if possible. So we put in our a sub k, we put in our b sub k, we cross multiply, and that is true. We know, by the time you're in Calc 2, you know how to graph the natural log function, you know how to graph the identity function. And so this is a fact that we know at this stage of the game. So this is true. Therefore, both diverge. So both will diverge. So we chose our b sub k. We've chosen our b sub k in 3 different ways now. One, we just got rid of constants that were added or subtracted. The next step up, we got rid of a function that was less intense than, less dominant than the dominant function. And then here, we're actually just kind of changing and using a different function. But it's closely related. If we're trying to show divergence, we know 1 over k diverges, so it's a natural function to take a look at. All right, one more slide in the comparison test section. Okay, top one. What function does this behave like?
1 over k to the 3.
1 over k to the 3. Behaves like it. That's just screaming comparison test. So now let's think about the direct comparison test. So if we're going to choose the b sub k to be 1 over k cubed, so if we're going to choose this to be 1 over k cubed, That's converging. So we identify P, it's bigger than 1, therefore it converges. All right. This denominator is bigger, right? That denominator is going to be bigger than this denominator. We're adding 3. So direct comparison should work. Well, let's find out. So for the direct comparison, or DCT, we want to show, let's see, convergence. So we want the A's to be smaller than the B's. That's what we want to show. The B's are the ones that we created. So we're going to have k to the 8 over k to the 11 plus 3. We don't know, but we want to show that this is true. And when we cross multiply, it comes out very fast. So we subtract off. We can always, usually we can get down to something that's very obvious by inspection. So here, this is true. Therefore, both are going to converge.
It's crazy that one little test can just make the really nasty looking function just.
It all falls out really nicely. Wait till we get to the next section.
Oh, no.
The next section has really, I think it's just amazing how quick we can get at the, with the next section we're going to do the alternating series test, and it's actually so fast.
I'm really frightened that my math professor just told me that it's super intriguing.
It's very intriguing. It is intriguing. Anytime you throw minuses into an infinite series, it gets intriguing. There's a very cool theorem that says if you have, we'll talk about the concept of absolutely convergent in the next section in a few minutes. And there's a theorem that says you can take any alternating, you can take any absolutely convergent series, rearrange the terms, and have it converge to anything you want it to converge to. Okay, but, all right, let's go to this one. So let's go to this thing. All right, so we know 1 over k squared converges. The numerator is bouncing closer and closer to pi over 2. I guess I shouldn't use the word bounce. It's climbing towards pi over 2. All right, so we know that the numerator, the limit of this is certainly 0. Denominator is going to infinity. The numerator is trapped less than pi over 2. So definitely is going to converge mentally. But to prove it, your mention that you could pick any constant you wanted is going to come into play here. So let's take a look at this. So the comparison test is a natural choice because we see the 1 over k squared. And so it makes sense that we could say, oh yeah, this is going to be a p series which is going to converge. All right? So if we choose p equals 2, that's greater than 1, therefore converge. So let's just put a 1 there for the time being. Put a 1 there. So that's our b sub k that we're choosing. And what we would want to show for the direct comparison test, we would want to show that the a's are smaller than the b's. So for convergence, we want to show that the a's are smaller than the b's. But when we plug in our a's right here, the b's are the ones, oh, whoops, the a is the one we're managing, the one we're analyzing. But that's not true if we choose a numerator of 1 for this. But what we know is that that numerator is always less than pi over 2. So if we just choose a constant that's bigger than pi over 2, so pi over 2 is,
6,
yeah, okay, let's pick 6.
68.
Okay, let's pick 68. Because you said so. 68. Any constant bigger than pi over 2. Any constant bigger than pi over 2. So if we pick 68, because Zach said 68 is his favorite number, that is now going to be a true inequality. So we have an infinite number of choices that would actually allow the direct comparison test to work really quickly. Because we multiply both sides by k squared, and the denominators vanish. And is inverse tangent of k smaller than 68? Yes. It's also smaller than 4 and 5 and 100 and a whole bunch of other things. So this is true. Therefore, both are going to converge. So we've kind of seen a whole bunch of different ways you can manipulate your b sub k. So all this constant has to be, because that's not going to change convergence, we just needs to be bigger than pi over 2. Actually, it could be equal to pi over 2 too.
Yeah. And even if,
I was thinking of integers.
and also even if tan k hit the asymptote, it still needs to be less than or equal to.
Yes, even if it touched that asymptote.
Even if it was like sine of k, where it goes to 1 and negative 1. If it's 1, it's still
Sufficient,
because
yep.
it's
Would
less
this
than.
only work for including vector functions, or is there
This works for any bounded function.
any bound?
So if this was sine of k over k squared, we could bound that anything that's greater than or equal to 1 would work for that too.
Or if it was like a, like a hyperbolic function that had like a peak
Had a
or
peak of
whatever
4.
at some point, as long as it's less than that at all points.
Exactly.
Still,
Then that would work. Yeah, so we could put in anything up there that,
It would be the same thing.
any bounded function up there.
peak
Any bounded
1,
function.
Anything above the apex.
Anything above that is.
All right, well, now that we understand inside and out all these series that have positive numbers,
Oh, yeah.
let's throw in some negatives. Let's
Now that we
sprinkle in
understand.
some negatives. So the sprinkling in of negatives, we're going to do it very systematically. We're going to sprinkle them in so that every other term is negative. We're not going to randomly sprinkle. We're going to say, okay, we're going to sprinkle very systematically. We're going to put a minus in every other position. And the first interesting thing is to consider the alternating harmonic. So once again, we've mentioned this before. This is just called the switch. All it does is change the sign from positive to negative. And the alternating harmonic is actually going to converge. The harmonic diverges, of course, but the alternating harmonic, if we look at it, first term is up here at 1, and then we subtracted a half, and we went down here. And then we added a third, and then we subtracted a fourth, and then we added a fifth, and we subtract a sixth, add a seventh, subtract an eighth. And you can see that the alternating harmonic is converging to some number right there. You actually know this number. So if we were to look at the sequence of partial sums, we have 1 and then a half, so 1 is the first one right up there, and then if we subtract a half, we're down at a half, and then if we add a third, we're up there, blah, blah, blah. So we get this sequence of partial sums. Looks like that. I can't show you this, but it turns out that the alternating harmonic converges to the natural log of 2.
Why not?
Why can't I show you? Because we don't have time.
Math secret.
It's a math secret. Got to keep some things hidden.
They wouldn't have world domination otherwise.
But it converges to natural log of 2, which is kind of, A, it converges, and B, it converges to something that can actually be calculated, which is kind of cool. So in order to prove that, you would have to be able to come up with your S sub n and be able to identify a pattern here. If you could identify a pattern, take the limit of it, and identifying that pattern is super hard. But it turns out the most important thing is that it converges. The interesting thing is it converges to a number that we know, natural log of 2. And if you do this kind of thing in Desmos and you graph natural log of 2, you'll see it just gets really, really infinitesimally close. So here is the alternating series test. Very simple. Some books actually have the alternating series test as just one statement. So this says alternating series. First, I want to point out a notational thing. A sub k is positive. A sub k is distinct from the switch. When we talk about an alternating series, we think of breaking apart the a sub k and the negative sign. So the a sub k is positive. And here's what the alternating series test says. It just says, and I mentioned this before, that this non-increasing, you can just think of it as decreasing. Totally fine to think of it as decreasing. So the terms of the series, if they are decreasing in magnitude, so decreasing in magnitude means that they're going down. So 1, 1/2, 1/3, 1/4, those are decreasing in magnitude. And the limit is 0. Done. So if the terms are decreasing in magnitude and the limit is 0, done. That's it. This, in my opinion, should be done first, because that's the divergence test. If the limit of a sub k is not 0, it diverges instantly. This is more tedious to show with algebra. That is simple to show. Why go through the hassle of this if this limit ends up not being 0? So I would put that one first and this one second. Because if a sub k's limit is not 0, you're kind of mentally thinking about that anyway. Then there's no need to even do the other thing. So here's how we prove that the alternating harmonic is convergent. So first step, the limit of a sub k for the alternating harmonic is the limit of 1 over k, which is 0. So that checks. So again, be very clear that the switch, this is not part of a sub k. A sub k is just the 1 over k part. The switch, ignore the switch. Now the second part is to show that the terms are decreasing in magnitude. So when we say the terms are decreasing in magnitude, we're thinking about, again, ignoring the minuses. We're trying to show that those are decreasing in magnitude. So to show that the terms are decreasing in magnitude, here's what WTS, here's what we want to show. We want to show, and I will write it in this direction. Now it's technically true that you have the equal to sign, but 99.9% of the time, really you could just say strictly greater than sign there. The terms are strictly getting less. This is the non-increasing thing. It is totally, if we can show something even stronger, then, then it's definitely going to converge. In our practice, the series that we're going to look at, that is totally sufficient. You could be more, kind of subtle and put the equal to sign there. It doesn't matter. But in your mind, what I want you to be thinking of is the terms are shrinking to 0. If the terms are shrinking to 0, your alternating series is going to converge. So all we have to do is show that the limit is 0 and that the terms are decreasing. That's all we have to show. All right, so we want to show the terms are decreasing. Well, a sub k is 1 over k. What's a sub k plus 1?
1 over k plus 1.
1 over k plus 1. So we multiply, cross multiply. So is that true? Heck yeah, that's true. So subtract off the k, get down to this numerical by inspection thing. This is true. So this checks. So therefore, we have convergence. So all we have to do is show that those two things are true. Limit is 0, and the terms are decreasing. So if the terms are decreasing and the limit is 0, then your alternating series converges. Some books, again, will put this in one statement. They'll say that the magnitude of the terms decrease to 0, something like that. Or decrease towards 0. So let's see. Here's another one. So in my opinion, the first step we should do is the limit step. So we're going to say the limit of a sub k, which is going to be the limit of 1 over the square root of k. So once again, the switch is not part of a sub k. That limit right there is 0. Let me get rid of that little thing. So that limit is 0. So first step, check. Second step, we want to show that it's decreasing. And to show that it's decreasing, we want to show this inequality. So I will write the inequality that way because I'm visualizing our sequence of terms going from right to left, getting smaller. You know, they write it the other way. That seems, you know, I would rather write it that way, show that that's true. It's the same idea though. So here is our 1 over square root of k. We want to show that that's bigger than 1 over square root of k plus 1. Cross multiply. And on the left we'll have square root of k plus 1. On the right, and these are all positive numbers here, so we don't have to worry about any inequality weirdness. Take the square of both sides. Subtract the k. Whoops. And we have an inequality that is true by inspection. So if both of those things are true, limit is 0, terms decrease, done. Converges. That's one of the simpler tests. And it's amazing that it's that quick. Any questions on either of the two steps that we want to show?
If one of them is not true, then is it divergent?
Then it's divergent, yep. If the limit is not 0, it's divergent, so that's the divergence test. And if the terms aren't decreasing, now it might be, I guess I should say that it's inconclusive, because if the limit is not 0, then for sure it diverges. But it would be possible to create a sequence of terms that isn't decreasing, it's got some little ripples to it, but does have a limit of 0, that it would be possible. So if the limit is 0, it definitely diverges. If this part fails, it's inconclusive, more correctly. Okay. There are fancy ways to make switches. That is a switch. This is an alternating series. It may not look like an alternating series, but it is. If we take and just sort of think about the values of cosine of pi k, let's write out the first few terms here. So the denominator is going to be 1 at first, and then when it goes to 2, it's going to be 4, and then 9. That should be enough terms. So plug in the k here of 1, cosine of pi, -1. And let's put that negative out here, so -1. Plug in a 2, cosine of 2 pi, +1, and then -1, and then plus ... So that is an alternating series. First, let's take the limit of a sub k as k goes to infinity. Well, a sub k has nothing to do with the switch. A sub k is just this part. take out the switch. Take out the switch for a sub k. So that limit is 0, so step 1 checks. Now we want to show that the sequence of terms is decreasing. So we want to show that as we go further out to the right, the terms are getting smaller. So that's what we want to show. So a sub k is 1 over k squared. So we want to show, is that bigger than 1 over k plus 1 squared? So a sub k plus 1, we plug in a k plus 1 for that k right there, and we get that. We cross multiply. We take the square root of both sides. Again, all these k's are positive. There's no funny business going on. We can take square roots. And if we want to get all the way down to the numerical inequality, that is true. So that checks, therefore converge. So alternating series test, pretty straightforward. Now sometimes with the alternating series test, this inequality thing can be really a pain in the butt. There is another way to show that a sequence is decreasing that you learned in Calc 1. So if we think about our sequence as being embedded within a continuous function, how do you show a continuous function is decreasing?
If the
What was that?
derivative is always, or
Derivative is
negative.
negative.
Yeah.
So you could also get at it that way. So it is technically possible. You could, in this step right here, or show f prime of x is negative with f of x equal to 1 over k squared. 1 over x squared if we're taking a derivative. So we could also do that. So let's take the derivative. So if we take the derivative here, this is x to the negative 2, so we get negative 2 x to the negative 1. You get that? Everyone follow that? Pull it up, x to the negative 2, pop down the coefficient. Ooh, did I do it right?
I think negative 3.
Negative 3. So that's going to be an x cubed right there. Well, for us, we are dealing with the x is corresponding to the k values. They're always positive. Right? We're off to the right of the y-axis, so all the x's are positive. This is negative. This is less than 0 for x greater than, for x greater than 0. That's true. So that's another way to do it. So therefore decreasing. So there are some times where the algebraic method will cause you a lot of consternation, and it would be possible to just take a derivative and show it's negative. That also shows the sequence of terms is decreasing. Okay, that thing. It's an alternating series, certainly. You all take the limit, do the 2 steps, and see if you can show that it is a convergent alternating series. We definitely know it's converging. Even if in your mind, you should be thinking of the minus as taking away from the cumulative value of the series, right? You can kind of think of it like a balloon type of thing. If you're adding air, it's getting bigger. If you're taking away some air, it's getting smaller. So negatives are taking away. So it's more likely to converge if there's negatives. And if this one had no negatives, it would definitely still converge. So if it's going to converge even with no negatives, it's got to converge if you sprinkle some negatives in there. All right, so see if you can get those 2 steps. Where are you going?
You might have to leave early.
What?
I feel sick, sorry.
Oh no! I hope you don't get anything nasty. There's been a few people around here that have gotten some pretty gnarly bugs this season. Hope you feel better.
Thank you.
Yeah. All right, so 2 steps there. See if you can get the 2 steps. I did the easy one first, while you're working on the hard one.
I see what you mean by the algebra being gross.
The algebra can get gross
Also-
when there's logs in there.
The doing it with a derivative doesn't seem any more fun, so I'm not gonna try.
So,
Derivative.
so this is what your thing should be looking like. And right away, you should be looking at it saying, oh, crap, nothing's gonna just cancel. Like in a lot of them, things just cancel, and that makes it so much more, you know, makes it just sort of work. So here's the strategy.
Well, you can actually make things cancel now if you distribute the.
Yeah, you could do some of those types of things. You could distribute the K and you could get a K to come out. But here is what I'm going to suggest. So I'm going to put the logs on one side. We'll just pick the left side for no great reason. No particular reason. So I'm putting the logs on the left and I'm putting the K's on the right. Okay, now on the left, you have this square that you could sort of pull off. Okay. Say again?
You could do log rules and subtract the k, and then k plus 1 minus k.
No. Oh, you're saying that if you did a log property?
Yeah, that's what.
Yeah, so remember that the log property, if you have this, you could turn that into log of A minus log of B, but do we have that?
We have it the other way around. We have an x.
We don't have 2 logs. Excuse me, we have 2 logs, not 1 log.
If it's
Like,
division.
the 2 logs would have to be subtracted to.
Oh, okay.
See what I mean?
It's backwards.
Yeah, it's
You can
not
split it out into log k times log 1, right? On the
Nope.
top?
Can't distribute the log
Oh, no,
function.
never mind, crazy.
Yeah, crazy.
Crazy.
So tell me this, what is the on the right-hand side, is that greater than or equal to 1? On the right-hand side.
It's less than 1?
Equal to
Oh, wait, no, it's equal.
On the right, it's less than 1, isn't it?
Yeah, it's less than 1.
Less than 1. So on this side, we always have a fraction. Truly a fraction, less than 1. Right? For every value of k, 100 over 101, it's always fractional. It's always less than 1. What about the right-hand side?
Slightly bigger than 1.
Bigger than 1, right? Because natural log of k plus 1, this is an increasing function. Right? The natural log function we know is increasing, looks like this. So if you have whatever, if you pick a k and you pick a k plus 1, natural log of k plus 1 is bigger than natural log of k. So this side is always greater than 1, and this side is always less than 1. So So if this is always greater than 1 and this is always less than 1, then the inequality must be true. So therefore converge. Yeah, so the algebra can get a little squirrely as soon as there's a natural log in there. And I think I heard that taking the derivative of this could be kind of messy, and the answer is yeah, the derivative of that is also messy. You would have to use the quotient rule with the product rule, but you could end up showing that it's negative. That would also work. So you could take f of x equals 1 over x natural log of x quantity squared and show f prime of x is negative. So you could also show that. Messy for sure. All right, speaking of messy, let's take a look at this messy one.
Oh, look, it's one you can't do derivatives of.
So we can't do derivatives here. So here we're going to take the limit of a sub k. So that's the limit of, again, I'm going to beat it into your head. A sub k for an alternating series doesn't include the switch. A sub k is always positive. And what is this limit here?
Okay, 0.
0. The power tower is the dominant function here. Power tower grows even faster than a factorial. And all we can do, though, is say by growth rates. So step 1 checks. And now we want to show that this sequence of terms is decreasing. So we want to show that the further we go out in the sequence of terms, they're getting smaller. That's what we want to show. So on the left, we have k factorial over k to the k. On the right, we're going to have k plus 1 factorial divided by k plus 1 to the k plus 1. Okay, so first, let's try to peel some stuff apart. And by that, here's what I mean. We can expand a little bit here on the right-hand side. K plus 1 factorial is the same thing as k plus 1 multiplied by k factorial. And if you have 6 factorial, that's the same thing as 6 times 5 factorial. Okay, everybody okay with that? And now what you should see is that, okay, well, the k factorials will cancel. Everything's positive, so you could divide both sides by k factorial. So those k factorials can go away. Those are gone. In the denominator, we can write this as k plus 1 to the k multiplied by k plus 1. K plus 1 to the k plus 1, these have the same base, and if you were to add the exponents, you would get back to where we were. Now, we have another thing canceling. This k plus 1 factor with that k plus 1 factor will cancel. And now we're close. So at this stage, let's summarize what we have. So let's see. If we were to cross multiply, we would have k plus 1 to the k on the left. We still have our greater than with a question mark. And if we cross multiply, this k to the k is going to come over to the right. So we have that. Now we can take the kth root of both sides. Since the powers are matching, you can kth root both sides. We end up with that. We end up with our, once again, numerical thing. So that's true. Therefore, converge. So the algebra can get a little bit unwieldy, but just stick with it. All right, so we showed both steps true, so that is a convergent series. This is what we would have expected it to converge. Even if this minus sign wasn't there, we would expect convergence because the k to the k dominates, so those terms are going to go to 0 very fast. Very, very fast. So we would expect that. Similarly here, if we took away that switch, we
have shown.
have shown that k over natural log of k squared, that this goes to 0 fast. These terms are going to go to 0 fast enough that we have convergence. So if you sprinkle in some minuses, it's just going to converge to something that's smaller, less than. Okay, so let's look at a visual thing for our last topic. The remainder for series is really, really important. But remainders for most series are a hassle to analyze. There is one exception. And that one exception is the alternating series. The remainder for an alternating series, bless you, is the simplest of all series to analyze. So we in this class, this is the only remainder we're really going to look at. When you get into numerical analysis or solving differential equations by computation or whatever, there's a million classes that you can take where you look at remainders in a more numerical way. We are going to just look at one. And so when we think about the remainder, think about it the way we talked about it earlier in the week. The remainder is, if we imagine having a convergent series, it doesn't make sense to talk about the remainder if the series diverges. The idea is that if the series converges, how far out do you have to go to get good accuracy? That's what our goal is, good accuracy. So the sum of the series is S, that's often unknown. S sub n is the sum of the first n terms, so we think of that as the leading terms. And the remainder is going to be the total sum minus the leading terms. It's essentially the sum of the tail. Okay, here is the remarkable fact. The remainder for an alternating series, all you have to do is look at the next term. That's what this is saying. So let me write this out in words. If we look at a convergent alternating series, so here is the alternating harmonic. We know it converges to the natural log of 2. So, if you look at these two terms, you add them up and you get 1/2. This is going to be within 1/3 of ln2. All you have to do is look at the next term's magnitude. If you add up the first 3 terms, so then you have 1/2 plus 1/3, which is going to be what, 5/6? If I've added correctly, 5/6. This is going to be within how much of natural log of 2? A quarter of natural log of 2. Because that's the next term. It's the first unused term. And you keep on going like that. If you add up the first 100 terms, you will be within, whatever the 101st term is, you'll be within that much of this total sum. So it's a very simple way to analyze the remainder, and here is the visual for it. So if your S sub n is right there, and this is where you're going to converge to, then this distance right here, that's your remainder, right? Your remainder is the difference between the sum and your S sub n. But the next term is going to take you from there all the way past what the sum of the series is to down there. So the a sub n plus 1 is that distance. And that distance is a little bit more than that distance, but it's a reasonable approximation to the actual remainder. So we know that it's a slight overestimate of the remainder. But it's a simple way to get at, a gauge on the remainder. All right, let's finish. We're done with week 10 or something like that. It just feels,
Nerds.
it feels fast.
Yeah, I'm just there.
I know. Home stretch. Home stretch. We only have chapter 11 and 12.
Another interesting thing on that is that it specifically states that it's not just a convergent alternating series, but it's also non-increasing, which means that there must be a way to make a increasing alternating series. Or not necessarily an increasing, but a non-decreasing,
Yes.
essentially.
Yeah, and so that's
That
where
would
you add
result
these
in-
little wiggles in.
Yeah, that's
So-
where like it goes up. But then what you'd see here as the remainder is not, because it would go down to like here first.
Yeah, so it's going to
and
be.
then go below.
Yeah, so we definitely need that piece
The
there.
non-increasing.
And-
But that's the only way we have to prove that it converges anyway. So,
When we think about our terms, this is going to be the visual that we should be thinking about for the magnitude of our terms. Because we can, it's like you can create, when you're dealing with real numbered functions, you can create all sorts of weird things. You can build functions that are continuous everywhere but nowhere differentiable.
those last three.
What? Continuous everywhere but nowhere differentiable. You think like a sawtooth type thing. Or you can build the most crazy functions with real valued functions. The interesting thing when you go on and if you take complex analysis and you look at complex valued functions, those are actually more predictable than real valued functions.
Cool.
Like what's really funny is that if you have a real valued function and you're moving along, just because you know what the value is here, if you go out to here, it tells you know nothing about this value necessarily by knowing its value here. And there's this bizarre theorem that complex valued function that's defined on a circle, on a disk, if you know what its boundary values are, you know what its value is at every point inside the circle. Which is
that makes sense.
Which is just bizarre to me. Like you can imagine a real valued function, if we've got a disk in the xy plane, you can imagine a paraboloid on top or paraboloid down below, you can imagine all sorts of undulations, but complex valued functions, you can't create those kind of anomalies. If you know what its values are on the boundary, you know what its values are everywhere on the inside. Totally different than real valued functions, which is, it's like,
Who needs real stuff?
right? It's like, well, how come those are so much more predictable? Oh, I just realized I hadn't stopped this thing.